Hello. In this notebook, I am demonstrating the TensorFlow low-level implementation of a basic neural network for nonlinear regression. The goal is to learn a nonlinear mapping from three input variables to one continuous output using a three hidden layer neural network. So this notebook includes synthetic data generation, validation test split, a 4D style visualization, manual low level, TensorFlow parameter definition, forward propagation, loss computation, and all the further steps that is required to complete. So in the first markdown cell, I have mentioned all the things that need to be done. In the next cell, I install the required libraries such as TensorFlow, scikit-learn, and Matplot library. TensorFlow is used for neural network computation. Scikit-learn is used for train, test, split, and PCA. And Matplot library is used to visualize the data and the training results. In this section, I import the required libraries and set the random seed for reproducibility. Then I define a function to generate a synthetic nonlinear regression data. The dataset contains three input variables, which is x1, x2, and x3. The target y is generated using a nonlinear equation that combines a trigonometry, polynomial terms, and interaction terms, and some added Gaussian noise. And this makes the problem realistic enough to test the neural network learning. Next, I combine the three variables into a future matrix X and reshape the target into a column vector. Then I split the data set into training set, validation set, and test set. The training set is used to learn the weights. The validation set is helps monitor generalization during training, and the test set is reserved for the final evaluation. Finally, I print the shapes of these data sets to verify the split. Next, in this cell, I visualize a synthetic data using a 4D style plot, and the problem has three input dimension and one output dimension, so overall fit is four dimensional. Since that I cannot directly cannot be plotted, I use a PCA to reduce the three input variables into three input components. Then I plot these three PCA component into 3D scatter plot and use the color of each to represent the target value y. So the x-axis is principal component 1, y is principal component 2, z is principal component 3, and the color shows the target. This is the main low-level setup section. Here I import TensorFlow and the TensorFlow random seed. Instead of using a high-level model APIs like sequential or functional API, I define the network parameters manually. So as we can see, these are the ones I have done here, and so after plotting this into like a 4D model, then I here I have converted NumPy arrays into TensorFlow tensor. Then I create a versions of training input and targets, validation input and targets, and test inputs. And this is necessary because the low level tensor level training process work directly with the TensorFlow tensors. Next, in this cell, this is a main low level model definition. Here I define the custom class called low level TFNet. Inside the constructor, I manually create the trainable parameters of the network W1 and B1 for the first hidden layer, and W2 to B2 for the second one, W3 B3 for the third hidden layer, W4 B4 for the output layer. So this is a neural network with three input features and three hidden layers and one output neuron for regression. I also define a property called trainable variable, so TensorFlow knows which parameter must be updated during the training. In the call method, I define forward pass manually. Each hidden layer performs a linear transformation using weights and bias followed by ReLU activation. The output layer performs only the linear transformation, since for regression we usually keep the final layer linear. One important point is that tf dot eindsum instead of standard matrix multiplication that satisfies the assignment requirement and still performs the same linear transformation. After creating the model object, I define the Adam optimizer with the learning rate of 0.01 and the loss function as mean squared error. Next, this cell contains the custom training loop. The first I set the number of epochs as 500 and create the two lists to store the training loss and validation loss. Then for epoch, I use tf.gradient tape. Inside the tape block, I run the forward pass on the training data, compute the predictions, and then calculate the mean squared error loss. After that, I use tape.gradient to compute gradient of the loss with respect to all trainable model parameters. Then I apply the gradients to gradient apply those gradients using the optimizer. Then next I run the model on the validation data and compute the validation loss. I store both this training loss and validation loss after every epoch. Finally, every 100 epochs, I print the current epoch number along with the loss training and validation loss. This is the low level TensorFlow equivalent of model dot fit and does automatically in high level APIs. In this cell, I plot a training and validation loss curves. The x-axis shows the epoch number and the y-axis shows the mean squared error loss. This plot helps me check whether the model is learning properly. If both curves decrease over time and stay reasonably close, that is usually indicates a good learning and decent generalization. So in this cell, I define a helper function called a regression report. Regression report. This function calculates standard regression metrics, which is mean squared error, root mean squared error, and mean absolute error. R square, which shows how well the model explains the variance in the data. I flatten both true and predicted values first so the calculation works cleanly. This helper function makes the final evaluation section more organized. In the final code cell, I evaluate the train model on the test data. So I generate a prediction for the first test unit using the train network. And then I call the regression report function to print the final regression metrics. After that, I create a scatter plot of true target values versus predicted values. If the model performs well, the point should lie close to ideal diagonal trend. So this final cell gives both numerical visual evaluation of the model performance on screen, on unseen data. So to summarize, this notebook builds a 3 hidden layer nonlinear regression network using a low level TensorFlow. That's it with this demo. Thank you.